Upper Yukon Territory, 1897. While fellow prospectors raced to pitch their standard canvas tents before the killing cold arrived, Ontario carpenter John M. was still digging, excavating and piling snow into a massive 8-foot mound. His fellow trappers called it wasteful. They laughed at his snow house foolishness. Why waste days building when a proven canvas tent and stove had served frontier camps for decades? Then April 1898 brought the test. 48 hours of relentless blizzard, winds gusting to 50 miles per hour, temperatures holding steady at 40 below zero. Canvas tents collapsed under snow loads. Families burned through 8 logs per man just to survive in mid-teen degree interiors. 5 men suffered frostbite. But John M.'s foolish snow mound maintained 25 degrees while burning a single log per person. What did this former mill carpenter understand about winter survival that generations of frontier wisdom had completely missed? The canvas tent that killed William Garrett measured 8 feet by 10 feet, standard issue from the Hudson Bay Company catalog. Garrett, a seasoned prospector from Michigan, had pitched it according to frontier protocol on a gentle slope above Bonanza Creek in late November of 1897. The tent's duck canvas walls, treated with paraffin for water resistance, promised reliable shelter through the Yukon winter. Company literature guaranteed performance to 20 below zero with proper stove management. Garrett never saw 20 below. On December 15th, when exterior temperatures dropped to 38 below, his tent's interior registered minus 12 degrees despite burning split spruce continuously in his Yukon stove. Ice formed on the canvas walls 6 inches thick. His breath froze and fell as snow onto his sleeping furs. By morning, frost covered every surface inside the tent, including his rifle barrel and the coffee pot beside his bedroll. The moisture from his breathing and cooking had condensed, frozen, and created a miniature ice cave within the canvas walls. 3 tents down the ridge, Samuel Morrison faced similar conditions. His canvas shelter, identical to Garrett's, required 4 armloads of dry firewood every 6 hours just to maintain interior temperatures above zero. The duck canvas, stretched tight in autumn, had shrunk and split along 2 seams as moisture froze and expanded within the weave. Cold air poured through these gaps, creating drafts that made sleep impossible, even wrapped in caribou hide and wool blankets. Morrison calculated his fuel consumption at 12 cords of wood per month, triple his original estimate. The mathematics of canvas tent failure revealed themselves in precise measurements. Standard frontier canvas, woven from cotton duck, provided an insulation value equivalent to a heavy wool coat. In still air at moderate temperatures, this sufficed. But Yukon winds averaged 15 miles per hour through winter months, creating convective heat loss that overwhelmed any heating system smaller than a full cabin stove. Canvas tent occupants required constant fire maintenance, burning through limited wood supplies and facing carbon monoxide poisoning risks in poorly ventilated shelters. John M. observed these failures with the analytical eye of a millwright. His carpentry training at the Thompson Lumber Mill in Kingston, Ontario, had taught him to calculate heat loss through building materials. He understood thermal bridging, where metal tent stakes and frame poles conducted heat directly from interior to exterior. He recognized the fundamental flaw in canvas tent design for extreme cold. The shelter fought against the environment rather than working with it. His education in alternative methods had begun 3 winters earlier during a trapping expedition with Naki K, a Koyukon guide from the Porcupine River drainage. Naki had demonstrated the Quinji, an Athabascan snow shelter built by piling loose snow into a dome and hollowing out the interior. The technique seemed primitive to John M.'s European-trained eye, but the mathematics intrigued him. Snow, when properly compacted, trapped air in thousands of tiny pockets, creating insulation values far superior to canvas. The Koyukon method required specific snow conditions and precise timing. Naki explained that fresh powder snow, too light and airy, would not compact properly. Old, wind-crusted snow became too dense and difficult to excavate. The ideal building snow fell during moderate temperatures, around 10 to 20 degrees Fahrenheit, creating crystals that bonded when compressed but remained workable for shaping. John M. had attempted his first Quincy during that expedition, following Naki's instructions to pile snow 6 feet high in a rough dome shape. The initial construction took 8 hours of steady work with snowshoes and a grain shovel. After allowing the pile to settle overnight, he began excavation, removing snow from the interior until walls measured approximately 18 inches thick. The finished shelter, crude but functional, maintained interior temperatures 30 degrees warmer than outside air. But his early attempts revealed critical gaps in technique. His first Quincy suffered from poor snow selection. Working with wind-packed snow from a ridgetop, he found the material too hard to compact evenly and too brittle for smooth wall shaping. Interior surfaces remained rough and prone to dripping as body heat warmed the walls. The entrance, excavated at the same level as the sleeping platform, allowed cold air to flow directly into the living space. His second attempt, built during the following winter, incorporated lessons learned from both failure and observation. He selected building snow from a protected hollow where wind had not crusted the surface. The pile construction went more smoothly, but his excavation technique remained flawed. Walls varied in thickness from 8 inches to 2 feet, creating weak points where collapse threatened and thick sections that wasted labor. Jakob H., a Swiss immigrant carpenter working the same trap lines, provided crucial refinement to John M.'s technique. Jacob had built snow shelters in the Alps during his youth, using methods developed over centuries of winter survival. He demonstrated proper wall thickness measurement using a birch probe marked in 1-inch increments. Walls thinner than 10 inches risked collapse under load. Walls thicker than 16 inches wasted excavation effort without significant thermal improvement. The Swiss method also addressed interior finishing. Jakob showed how to smooth walls using a heated metal plate, melting the surface slightly to create a glazed interior that shed moisture rather than absorbing it. This glazing technique prevented the dripping problem that plagued John M.'s early shelters. The smooth surface also reflected body heat back into the living space rather than absorbing it into rough snow crystals. Despite these improvements, John M.'s third Quincy still fell short of his requirements. The entrance design, copied directly from Naki's demonstration, created a thermal chimney effect that drew warm air from the sleeping area. Cold air settled in the entrance tunnel, but mixed with heated air from the interior, creating uncomfortable drafts and reducing overall thermal efficiency. He needed a better understanding of air movement within the shelter to solve this circulation problem. The social response to his experiments proved as challenging as the technical difficulties. Fellow trappers viewed his snow construction with suspicion bordering on ridicule. Thomas R., the supply camp foreman, openly mocked John M.'s Eskimo foolishness during evening gatherings around the communal fire. The foreman argued that proven frontier methods existed for good reasons, tested by decades of successful winter camps throughout the Northern Territories. The January storm of 1898 revealed the fatal flaw in standard frontier campsite selection. Samuel Morrison had pitched his tent on the exposed ridge above El Dorado Creek, following accepted practice of choosing elevated ground to avoid flooding and maintain visibility of the surrounding territory. The location offered strategic advantages during moderate weather, but when Arctic winds began channeling through the valley at 35 miles per hour, his elevated position became a liability. Wind scour across the ridgetop created a Venturi effect, accelerating airflow and stripping away the insulating layer of still air that surrounded his canvas walls. Morrison measured wind speeds of 42 miles per hour at his tent site, while the protected hollow below recorded gusts of only 18 miles per hour. The mathematical relationship between wind speed and heat loss followed an exponential curve. Doubling wind speed increased convective heat loss by a factor of 4, transforming a manageable heating challenge into an impossible fuel consumption spiral. Cold air drainage compounded the wind exposure problem. Dense, frigid air flowing down from the surrounding peaks pooled in the valley bottom during calm periods, but ridgetop locations caught the full force of katabatic winds that developed as this cold air mass gained momentum flowing downhill. Morrison's thermometer readings showed his ridge site averaged 8 degrees colder than protected locations at the same elevation, before accounting for wind chill effects that drove apparent temperatures even lower. John M. recognized these microclimate patterns from his lumber mill experience in Ontario, where winter logging operations required careful campsite selection to minimize fuel costs and weather exposure. But the specific techniques for reading Yukon terrain demanded local knowledge that only Indigenous guides possessed. Naki K demonstrated site evaluation methods developed through generations of seasonal hunting camps in similar conditions. The Koyukon approach to site selection began with snow pattern analysis. Naki showed John M. how to read wind direction and intensity from snowdrift formations around rocks and trees. Windward surfaces accumulated hard-packed snow in distinct ridge patterns, while leeward sides collected soft, deep deposits that indicated calm air zones. These snow signatures revealed prevailing wind patterns over weeks and months, not just current conditions. Tree growth patterns provided additional wind mapping data. Spruce and fir trees on exposed slopes grew with pronounced lean away from prevailing winds, their branches stripped and stunted on the windward side while maintaining full foliage in protected zones. Nike taught John M. to identify these wind shadows, areas of reduced air movement that extended downwind from natural barriers like rock outcrops, dense tree stands, and hillside folds. The ideal snow shelter location lay within such a wind shadow, positioned on the leeward side of a natural windbreak, but elevated enough to avoid cold air pooling in the valley bottom. Naki selected a site 40 yards downhill from a dense stand of mature spruce trees, protected from northwest winds but elevated 12 feet above the creek bottom where cold air settled during calm nights. The location received morning sun exposure to aid in snow construction, but remained shaded during afternoon hours when solar heating could destabilize shelter walls. Jacob H. contributed alpine techniques for enhancing natural wind protection through artificial barriers. He demonstrated snow wall construction, building a crescent-hape wind fence uphill from the shelter site using blocks cut from compacted snow deposits. These walls, built 3 feet high and 18 inches thick, deflected incoming wind flow upward and created an enlarged zone of calm air around the construction area. The wind fence technique required specific geometry to function effectively. Jacob calculated the protected zone behind a 3-foot wall extended downwind for approximately 21 feet, based on alpine engineering principles developed for avalanche barriers in the Swiss Alps. The wall's curved design prevented wind from wrapping around the ends and creating turbulence within the protected area. Entrance orientation demanded equally precise calculation. Standard practice placed tent doors facing away from prevailing winds, but snow shelter entrances operated on different principles. The tunnel entrance needed to face perpendicular to dominant wind direction, preventing direct wind penetration while avoiding the creation of negative pressure zones that could draw warm air from the interior. John M. oriented his entrance tunnel toward the southeast, 90 degrees offset from the prevailing northwest winds, but angled to catch indirect sunlight during morning hours. This positioning prevented snow accumulation that could block the entrance while maintaining protection from direct wind exposure. The tunnel itself required specific dimensions to function as an effective cold trap, with the entrance floor excavated 18 inches below the interior sleeping platform level. Construction of wind barriers and proper site preparation added significant labor to shelter building time. John M.'s refined site selection and preparation process required 2 full days compared to the 2-hour tent setup used by his companions. The first day involved site evaluation, snow condition testing, and wind barrier construction. The second day focused on snow pile construction and initial compaction, allowing the mass to settle overnight before excavation began. The investment in site preparation proved worthwhile during the late January blizzard that tested every shelter in the Bonanza Creek district. Winds sustained at 40 miles per hour with gusts reaching 55 miles per hour created impossible conditions for exposed campsites. Morrison's ridgetop tent site recorded exterior temperatures of 42 below zero, with wind chill effects driving apparent temperatures below minus 70 degrees. John M.'s sheltered location, protected by natural windbreaks and artificial snow barriers, experienced exterior temperatures of 38 below zero with minimal wind chill effects in the immediate shelter vicinity. His thermometer, positioned at the tunnel entrance, recorded actual air temperatures rather than wind-adjusted readings. The 4-degree difference in actual temperature, combined with elimination of wind chill effects, created dramatically different heating requirements. Interior temperature measurements revealed the compound benefits of proper site selection. Morrison's canvas tent, fighting both extreme cold and constant wind exposure, achieved interior temperatures of only -11 degrees Fahrenheit despite burning seasoned spruce logs continuously in his camp stove. Ice formed on interior surfaces faster than his heating system could melt it, creating a feedback loop of increasing heat loss through enhanced thermal bridging. John M.'s snow shelter, positioned in the protected microclimate created by careful site selection, maintained interior temperatures of 16 degrees above zero using 1/3 the fuel Morrison consumed. The combination of wind protection and cold air drainage management created heating conditions that made the snow shelter technique viable rather than merely survivable. The structural collapse of William Chen's snow cave on February 3, 1898, demonstrated the critical importance of wall thickness calculation in snow shelter construction. Chen, a prospector from California, had attempted to replicate John M.'s shelter design, but excavated his walls to only 6 inches thick in an effort to maximize interior space. The reduced wall thickness created structural weak points that failed under the weight of fresh snowfall, burying Chen's sleeping furs and forcing him to abandon the shelter for a backup canvas tent. John M. had learned precise wall thickness requirements through systematic testing during the previous winter season. His measurements revealed that snow walls thinner than 10 inches lacked sufficient structural integrity to support overhead loads from additional snowfall or wind-deposited snow. Walls exceeding 16 inches provided diminishing returns in both insulation value and structural strength, while requiring excessive excavation labor that depleted energy reserves needed for other survival tasks. The optimal 12-inch wall thickness emerged from calculations based on snow density and compaction ratios. Fresh snow typically measured 8 to 12 pounds per cubic foot, but the sintering process increased density to 25 to 30 pounds per cubic foot in the structural shell. This density provided adequate load-bearing capacity while maintaining the air pocket structure that created insulation value. Jacob H. had taught John M. to test wall density using a birch probe weighted with lead shot, measuring penetration resistance to gauge compaction levels. Sintering timing proved equally critical to structural integrity. John M. discovered that excavation begun too early before snow crystals had time to bond, resulted in walls that crumbled during carving. Snow piled during temperatures above 20 degrees. Fahrenheit required minimum settling time of 4 hours. Snow constructed during colder conditions below 10 degrees needed 8 to 12 hours for adequate crystal bonding to develop. The sintering process itself involved complex crystalline changes, invisible to casual observation. Individual snow crystals, when compressed in the pile, began forming connecting bridges through sublimation and refreezing. Water vapor from the crystal surfaces migrated to contact points between adjacent crystals, where it refroze and created structural bonds. Temperature fluctuations during the settling period enhanced this process, with slight warming during daylight hours, accelerating sublimation, followed by rapid bonding during nighttime cooling. Interior shaping techniques developed by Jacob H. addressed moisture management problems that plagued early shelter attempts. Standard excavation methods created rough interior surfaces with countless small projections and depressions. These irregular surfaces provided nucleation sites where water vapor could condense and freeze, creating ice deposits that reduced interior air temperature and created uncomfortable dripping as body heat gradually melted the accumulations. The Swiss Alpine method required systematic wall smoothing using heated metal tools. Jacob demonstrated the technique using a cast iron camp skillet heated over a small fire outside the shelter. The heated metal, applied carefully to interior surfaces, melted a thin layer of snow that immediately refroze as a smooth, glazed surface. This glazing eliminated rough projections while creating a vapor barrier that prevented moisture infiltration into the snow matrix. Dome geometry calculations determined optimal interior shape for both structural strength and thermal efficiency. Jacob had learned alpine engineering principles that applied mathematical ratios to snow construction. The interior height at the center point should measure no more than 2/3 of the exterior base diameter to maintain structural stability. For John M's shelter design with a 12-foot base diameter, the optimal interior height measured 8 feet at the dome center. The domed shape distributed structural loads evenly across the wall surfaces, preventing stress concentrations that could cause localized failures. Additionally, the curved ceiling encouraged air circulation patterns that distributed heat evenly throughout the interior space. Flat or angular ceiling sections created dead air zones where cold pockets developed and reduced overall thermal efficiency. Excavation sequence followed specific protocols to maintain wall thickness uniformity. John M. began removal from the planned entrance location, working inward and upward following the intended dome curve. He used a wooden grain shovel with the blade edge sharpened to cut clean surfaces in the compacted snow. Metal tools conducted too much heat from his hands and created rough surfaces that required additional smoothing work. Wall thickness measurement during excavation required constant monitoring to prevent weak spots. John M. used birch probes cut to 12-inch lengths, pushing them through the wall from the interior to gauge thickness at multiple points around the dome circumference. Areas measuring less than 10 inches required additional snowpacking on the exterior surface before work continued. Areas exceeding 14 inches could be carefully thinned to reduce excavation labor. Interior bench construction integrated with the dome excavation process rather than representing a separate construction phase. The sleeping platform, carved 18 inches above the entrance floor level, utilized the natural dome geometry to create a level surface without requiring additional structural support. John M. shaped the bench surface with a slight backward slope of 2 degrees to prevent occupants from rolling forward during sleep while maintaining comfort for extended rest periods. Thermal mass calculation revealed the relationship between snow volume and heat storage capacity. The completed shelter contained approximately 40 cubic yards of compacted snow in the walls and dome structure. At 28 pounds per cubic foot density, the total thermal mass measured over 30 tons. This massive heat sink absorbed warmth from occupant body heat and small fires, storing the energy and releasing it gradually as interior air temperatures dropped. The thermal mass effect explained why properly constructed snow shelters maintained stable interior temperatures long after heating sources were extinguished. John M. measured temperature retention in his completed shelter, finding that interior air cooled only 6 degrees during an 8-hour period without any heat input. Canvas tents, lacking thermal mass, experienced temperature drops of 20 to 30 degrees during equivalent periods. Surface finishing work addressed condensation management through precise ice glazing techniques. After completing the basic excavation and smoothing, John M. applied final glazing using a heated copper plate borrowed from Jacobs mining equipment. The copper, heated to approximately 200 degrees Fahrenheit, melted surface snow to a depth of 1/8 inch. This melted layer immediately refroze as clear ice, creating a moisture-impervious interior surface. The glazed surface reflected radiant heat back into the interior space rather than absorbing it into the snow matrix. Additionally, the smooth ice prevented water vapor from condensing on interior surfaces, eliminating the dripping problems that made early shelters uncomfortable during extended occupancy periods. John M. found that proper surface glazing reduced interior humidity levels by 30% compared to unfinished snow walls. Construction time for the complete structural shell, including excavation and finishing work, averaged 14 hours of steady labor spread across 3 working days. The extended timeline reflected careful attention to wall thickness, monitoring, systematic surface smoothing, and proper thermal mass development rather than inefficient work methods. The thermal stratification failure of Robert Harrison's snow shelter on February 20th revealed the critical importance of interior air management in extreme cold survival. Harrison, a veteran trapper from Minnesota, had constructed his shelter using John M.'s structural techniques, but neglected the raised platform design, excavating his sleeping area at the same level as the entrance tunnel. Cold air flowing through the tunnel entrance mixed directly with warm air from his body heat and small cooking fire, creating turbulent circulation that prevented stable temperature zones from developing. John M. had discovered the principles of thermal layering through systematic temperature measurements within his completed shelter. Using a mercury thermometer suspended at different heights, he documented temperature variations of 12 degrees between floor level near the entrance and the sleeping platform area. Cold air, being denser than warm air, naturally settled in the lower tunnel section, while heated air rose and accumulated in the dome's upper portions around the raised sleeping bench. The two-zone system required precise elevation calculations to function effectively. John M.'s sleeping platform, carved 18 inches above the tunnel floor, positioned occupants within the warm air layer while maintaining the cold trap effect in the entrance area. Naki K had explained this principle using smoke from burning birch bark, demonstrating how heated air rose and accumulated in distinct layers, rather than mixing uniformly throughout the interior volume. Temperature differential measurements revealed the dramatic effectiveness of proper thermal zoning. John M. recorded entrance tunnel temperatures of 8 degrees above zero, while simultaneous readings at the sleeping platform measured 26 degrees above zero during February conditions with exterior temperatures of 35 below. The 18-inch elevation difference created an 18-degree temperature gradient that made the difference between survival and comfortable occupation. Heating system optimization eliminated the fuel consumption problems that plagued standard frontier shelters. Rather than fighting constant heat loss through canvas walls, John M.'s approach utilized the snow shell's thermal mass to store and redistribute heat energy. A small fire burning for 2 hours in a portable sheet metal firebox heated the thermal mass sufficiently to maintain comfortable temperatures for 8 hours without additional fuel input. The heating sequence followed specific timing protocols developed through winter-long experimentation. John M. lit his heating fire 1 hour before retiring, allowing the combustion heat to warm the interior air and begin heating the snow wall's inner surface. The glazed walls absorbed this thermal energy without melting, storing it in the crystalline structure for gradual release throughout the night. Peak thermal storage occurred approximately 90 minutes after fire ignition, indicated by wall surface temperatures reaching 32 degrees Fahrenheit. Body heat contribution provided substantial additional thermal input, often overlooked in conventional heating calculations. An adult human at rest generated approximately 300 BTUs per hour through metabolic processes. Within John M.'s insulated shelter environment, this body heat raised interior air temperature by 4 to 6 degrees above levels achievable through shelter design alone. Multiple occupants multiplied this effect proportionally, with 3 men generating sufficient heat to maintain comfortable sleeping conditions without any supplemental fire. Fuel consumption analysis revealed dramatic efficiency gains compared to canvas tent heating requirements. John M.'s thermal management system required 1/4 cord of seasoned spruce per month to maintain comfortable living conditions during continuous occupation. Morrison's canvas tent, fighting constant heat loss, consumed 3 cords monthly for barely survivable interior temperatures. The snow shelter's thermal mass effectively multiplied heating efficiency by a factor of 12. Moisture control demanded careful ventilation management to prevent interior humidity problems without losing accumulated heat. Water vapor from breathing, cooking, and melting snow for drinking accumulated in the sealed shelter environment, creating condensation problems if not properly vented. John M. Sakram carved a ventilation hole 3 inches in diameter at the dome's highest point, allowing moisture-laden air to escape while minimizing heat loss through convective circulation. The ventilation hole required adjustable closure capability to maintain optimal air exchange rates. John M. fashioned a plug from tightly packed snow that could be partially or completely removed depending on interior humidity levels and occupancy conditions. Full ventilation during cooking operations prevented steam accumulation, while partial closure during sleeping hours conserved heat while allowing adequate air exchange for comfortable breathing. Interior humidity measurement using Jacob H's mining hygrometer demonstrated the relationship between ventilation and moisture control. Sealed shelter conditions reached relative humidity levels of 85%, causing uncomfortable dampness in clothing and bedding. Partial ventilation reduced humidity to 60% while maintaining interior temperatures within 3 degrees of sealed conditions. Full ventilation during cooking operations prevented humidity spikes that could create ice formation on interior surfaces. Occupancy scheduling maximized thermal efficiency through coordinated heating and body heat utilization. John M. developed a routine where cooking and heating activities occurred during late afternoon hours, building thermal mass heat storage for nighttime use. Multiple occupants retired simultaneously to concentrate body heat generation during peak heat loss periods after midnight, when exterior temperatures typically reached their daily minimum. Sleep system integration utilized the thermal characteristics of the raised platform for maximum comfort and warmth. John M. arranged his sleeping furs and blankets to take advantage of warm air accumulation around the platform level while avoiding cold air circulation near the entrance tunnel. A caribou hide ground cloth provided insulation from direct contact with the snow platform, while wool blankets and fur robes trapped body heat in the warm air zone. Cooking system adaptation eliminated the carbon monoxide risks associated with enclosed fire operations while maintaining thermal efficiency. John M. used his portable firebox for heating and initial cooking operations, then moved food preparation to a small alcohol burner that produced minimal combustion byproducts. The alcohol burner provided sufficient heat for melting snow, brewing tea, and warming preserved foods while adding beneficial moisture to the dry interior air. Temperature monitoring throughout 24-hour cycles revealed optimal thermal management timing. Interior temperatures peaked at approximately 8 p.m., 3 hours after sunset heating operations, reaching 28 degrees above zero when exterior readings measured 40 below. Minimum interior temperatures occurred at 6 a.m., measuring 22 degrees above zero, representing a temperature swing of only 6 degrees compared to exterior variations of 15 degrees during the same period. The integrated thermal management system transformed snow shelter occupation from survival endurance to comfortable winter living. John M. documented sleeping quality improvements, noting that he achieved full night's rest without waking from cold-related discomfort, contrasted with canvas tent conditions that required periodic awakening for fire maintenance and warming activities. The April blizzard of 1898 arrived with unprecedented severity, catching the Bonanza Creek mining district during the critical transition between winter and spring operations. Weather conditions on April 15th began deteriorating rapidly as warm Pacific air masses collided with Arctic continental air over the Yukon Territory. Barometric pressure dropped from 30.2 inches to 28.6 inches in 18 hours, indicating an approaching storm system of unusual intensity for late-season weather patterns. The storm's timing proved particularly devastating for canvas tent operations throughout the district. Many prospectors had already begun spring preparations, reducing their firewood stockpiles and switching to lighter gear in anticipation of warmer weather. Thomas R.'s supply camp inventory showed fuel reserves calculated for moderate April conditions rather than extended winter storm operations. When temperatures plummeted to 41 below zero on April 16th, accompanied by sustained winds of 45 miles per hour, existing fuel supplies proved catastrophically inadequate. Structural failures began occurring within 12 hours of storm onset. The El Dorado Creek tent camp, housing 14 men in 7 canvas shelters, experienced 3 complete tent collapses during the first night. Wind-driven snow accumulated on tent surfaces at rates exceeding the structural capacity of standard frontier tent designs. Canvas duck fabric, already weakened by 4 months of winter freeze-thaw cycles, split along stress points where metal grommets concentrated loading forces. Morrison's detailed weather log documented the storm's progression and its effects on conventional shelter systems. Wind speeds peaked at 52 miles per hour during the second night, creating ground blizzard conditions where snow particles traveled horizontally at tremendous velocities. These conditions made outdoor movement impossible and prevented tent occupants from reaching emergency fuel supplies stored outside their shelters. Interior tent temperatures dropped to minus 18 degrees Fahrenheit despite continuous burning of emergency furniture and equipment. Fuel consumption calculations revealed the mathematical impossibility of maintaining survivable conditions using standard heating methods during the storm. Canvas tent occupants burned through 8 cords of seasoned spruce in 48 hours, exhausting monthly fuel allocations in 2 days. Even this massive fuel consumption failed to prevent hypothermia conditions, with several men showing early frostbite symptoms on extremities despite remaining inside heated shelters throughout the storm period. John M.'s integrated snow shelter system faced identical weather conditions from a protected site 40 yards from the main tent camp. His weather instruments recorded exterior temperatures of 40 below zero, with wind speeds of 38 miles per hour in his sheltered location. The storm deposited 22 inches of additional snow on his shelter's exterior, actually improving insulation values by increasing thermal mass and reducing air infiltration through any remaining gaps in the structure. Performance measurements during the storm demonstrated the complete effectiveness of proper snow shelter designed under extreme conditions. Interior temperature readings taken every 4 hours showed remarkable stability, with variations of only 3 degrees throughout the 48-hour storm period. Average interior temperature measured 24 degrees above zero, while exterior conditions averaged 40 below, creating a sustained 64-degree temperature differential. The shelter's structural integrity improved during the storm as additional snow loading compressed the dome structure and eliminated minor settling gaps that had developed during the winter months. Wind-driven snow filled exterior surface irregularities, creating a smoother aerodynamic profile that reduced wind resistance and prevented the formation of destructive pressure differentials that destroyed canvas structures. Fuel consumption analysis revealed the dramatic efficiency gains achieved through proper thermal mass utilization. John M. burned 1 1/2 cords of split spruce during the entire storm period, less than 20% of the fuel consumed by tent camp occupants. The heated thermal mass stored energy from this modest fuel input and released it gradually throughout each 24-hour cycle, maintaining comfortable living conditions without continuous fire maintenance. 6 additional men sought shelter in John M.'s structure during the second night as tent failures mounted throughout the district. The shelter's expanded capacity accommodated 9 total occupants without significant temperature reduction, as additional body heat generation offset increased air volume and moisture production. Interior space organization, with the raised sleeping platform and organized gear storage, provided adequate room for emergency occupancy levels. Medical outcomes documented the life-saving effectiveness of proper shelter design during extreme weather events. Tent camp occupants suffered 12 cases of superficial frostbite, 3 cases requiring medical evacuation to Dawson City for treatment of deep tissue freezing injury. Several men showed symptoms of carbon monoxide poisoning from desperate attempts to increase interior heating through inadequate ventilation of combustion appliances. John M.'s shelter occupants experienced 0 weather-related injuries during the storm period. Medical examination conducted by the district mining company doctor after the storm found no evidence of frostbite, hypothermia, or respiratory problems among shelter occupants. The controlled interior environment prevented the extreme physiological stress that caused medical emergencies in conventional shelters. Economic impact calculations revealed substantial cost advantages beyond simple survival considerations. The tent camp lost 6 working days due to medical evacuations, equipment replacement, and recovery time after the storm. Replacement costs for destroyed tents, damaged equipment, and emergency medical transport totaled over $400 in 1898 currency values. John M.'s operation resumed normal mining activities immediately after storm conditions cleared on April 18th. His shelter required no repairs or replacement equipment, and occupant health remained excellent throughout the emergency period. The economic advantage of reliable shelter performance during extreme weather events proved as significant as the survival benefits. Thomas R.'s formal recognition of John M.'s shelter system marked the beginning of widespread adoption throughout northern mining camps. The supply camp foreman documented detailed construction specifications and performance data for distribution to other company operations. His technical report, filed with the Canadian Mining Company headquarters, recommended snow shelter construction training for all winter camp supervisors operating above 60 degrees north latitude. Knowledge transfer accelerated through systematic documentation and training programs. John M. prepared illustrated construction manuals showing site selection criteria, wall thickness calculations, thermal management procedures, and occupancy protocols. These manuals reached mining camps throughout Alaska and northern Canada within 2 years of the April storm validation. Jacob H. carried the techniques back to European alpine communities during his return journey in 1900. Swiss mountain rescue organizations incorporated snow shelter principles into their emergency training curricula. Military engineering corps studying cold weather operations adopted modified versions of the thermal management systems for Arctic deployment scenarios. The integration of indigenous knowledge, immigrant craft traditions, and systematic experimental refinement created a winter shelter technology superior to conventional frontier methods. Modern cold weather survival manuals published by military and civilian organizations continue referencing the fundamental principles John M. Chang documented during his Yukon experiences, validating traditional knowledge through scientific measurement and systematic application.